So there's just two more surfaces that we need to talk about. We've already talked about cylinders, cylindrical paraboloids, we started talking about quadric surfaces, which were ellipsoids, hyperboloid of one sheet, hyperboloid of two sheets. Actually, we've got three more. No, we've got two more. We talked about the elliptic paraboloid. Do you guys have the elliptic paraboloid in your notes?
Yeah.
Yeah.
And we have
looks like a bowl, kind of.
And we have the hyperboloid with two sheets and one sheet.
Yes. So we've got two more that we're going to talk about. And then we'll just do some random examples where I give you an equation and we'll try to figure out what it is. And then we're also going to talk about spherical coordinates. And we'll see if we can get some done in the next section as well. But we got two more surfaces to talk about. So I'm not going to give you this the name for this yet. We're going to see if we can name it once we figure out the traces and see what it looks like. Then we'll name it. So just the general format is x squared over a squared plus y over b squared minus z squared over c squared equals 0. So we had a surface that had almost that exact same equation. There's one tiny difference here. Say it again. That would just change the orientation of it. That would change the direction that it's opening or the direction that it's pointing. It's the 0 that's different. We had this before where it was equal to 1. And that created a hyperboloid of two sheets. What was it?
One sheet.
Of one sheet. A hyperboloid of one sheet. So if it was equal to 1, it created a hyperboloid of one sheet. If it's equal to 0, it's going to create something completely different. So to figure out what this thing is, we're going to look at the traces. So to do the traces, remember, the easiest way to do it is to just set one of the variables equal to 0. That's going to give us what the cross sections look like in each of the individual two-dimensional planes. So for the xy trace, we're going to set z equal to 0, if that makes sense to do that. There are a few situations we said where setting the variable equal to 0 doesn't make sense, and instead we just set it equal to a constant. If we let z equal 0, then it just disappears from the equation, and we've got x squared over a squared plus y squared over b squared equals 0. The only time a sum of squares is equal to 0 is at the point 0, 0. But if you consider the possibility that z could also be a constant, if we just let z equal some constant and we add it over to the other side, That would be an ellipse. So when we're actually in the XY plane, all we have is a single point. But as we move away from the XY plane at parallel values of Z, we're starting to make these ellipses. And the Z values get bigger as you move farther away, which means the size of these ellipses get bigger. For the xz trace, we're going to let y equal 0. We get x squared over a squared minus z squared over c squared equals 0. If it was equal to 1, we'd say it's a hyperbola. But since it's equal to 0, we could actually do a little bit of algebra on this and simplify that equation.
Oh, just to guess.
Yeah. Not guess.
Or add Z squared
Add the
to
z squared over c squared over to the other side. If it's equal to 1, that wouldn't really help us at all. But since it's equal to 0, that helps.
Oh, it's multiple. I mean,
We could cross multiply.
That accomplishes anything.
It at least gets rid of the fractions.
One.
We're going to use an algebra operation. So we don't have an answer yet.
And then the squares.
Square root everything. Everything has a square right now. Z equals positive or negative c over ax. They're just lines. And there's no constant on the end of the line. Usually it goes through the origin, exactly. Usually the constant on the end of the line is the y-intercept, or in this case it would be the z-intercept, since it's in using the zx variables, which means it goes through the origin. It's not shifted up or down any. So lines that go through the origin, especially a pair of lines with opposite slopes like that, they're called radial lines. So this is just a pair of crisscrossing radial lines. And then look what happens when we set up our YZ trace. What is it? Same thing. Except instead of the X and the A, we've got a Y and a B. So we get Z equals plus or minus C over BY. So we've got another set of radial lines. The slope might be slightly different because of the B. It's in a different plane. It's in the YZ plane. So we've got these two sets of crisscrossing lines, and then we've got these ellipses. So in the xy plane, they come to a point. That's why we said when z equals 0, we just have a single point. But as we move away from the xy plane parallel, our slices are ellipses. So they might not be perfect circles. It could be, when we slice it horizontal, it could be wider than it is long. I only drew one set of radial lines, otherwise it's going to look all messy.
It's called what? Radial ellipses?
If you just look at the top piece, what does it look like?
Ellipse. Oh, what, a cone?
A cone, right. And then the cross sections are what? Ellipses. It's an elliptic cone. An elliptic cone.
With that, so all elliptic cones are mirrors?
They're actually two-sided, yes. In math, cones are always two-sided.
Oh, really?
Mm-hmm.
So what's the cone? Is there a special name for a cone that's one-sided? Absolute value, so
Yeah, you would either have to do absolute value or you would end up doing the square root and not include the plus or minus.
So it's not an ice cream cone.
An ice cream cone, mathematically, is technically only half of a cone.
Plus, yeah.
It's only half of a cone.
It's like an hour. It's like
You really want to use that somewhere, don't you?
What are those things called? The chip, the bugles. It's like two bugles.
Yes.
Or which figures?
So the hyperboloid of one sheet and the elliptic cone, the variable side of them looks exactly the same. The only difference is the hyperboloid of one sheet is equal to 1, because in our formula for hyperbolas, it's equal to 1. And then the elliptic cone, it's equal to 0. And that's how we're able to solve and get those radial lines in the traces, is when it's equal to 0. The last one is really, really tricky, and I cannot draw it.
What's it called?
I'm not going to tell you what it's called until after we look at the traces. But then I'm going to have to pull up, I can't draw it. That means you can? I've had students who could draw it, and they couldn't believe that I couldn't. Let me show you the equation and we'll talk about the traces. And then I will explain to you what this shape looks like. There are things that you know of. You already know what it is, don't you?
No, I mean, there's like 10 up here, and I'm just going to guess which one it is.
Okay.
Is it hyperbolic paraboloid?
Yes.
Yeah, I think it's
The hyperbolic paraboloid.
Yeah. That just, you can tell, that one is just like 100 times
So if we
different.
draw, we get $100.
If you can draw it, you automatically get 100 on your test.
Heck yeah.
Not really.
I'll take a shot at it.
That's it.
It's on the recording.
I've had students in the past who could draw it beautifully, and they tried to show me, and I still could not do it. I don't know why. I've just got this mental block. This thing looks like a Pringles chip. So if you think of the shape of a Pringles chip, that's exactly what it looks like.
Pringles chip is a mathematical.
It is. A saddle,
Yeah.
a horse saddle, is a hyperbolic paraboloid. Or I guess any type of saddle, anything you would put a saddle on, a camel. Do you put it?
Yeah, you can ride a camel.
Put a camel on that.
Yes.
Saddle person.
Shh. All right. We're going to look at the traces really quick. And then I'm going to pull a picture up from the internet because I can't draw it.
You gotta try.
I will try to draw it, and then I'm going to erase it really quickly and pull a picture up from the internet. XY trace.
It's a radial line.
We are not going to do radial lines on this one. We're going to do constants for Z. That's one thing that makes this one kind of tricky. Use a constant for Z. It's not an ellipse because of the subtraction. It's going to be a hyperbola because whatever the Z value ends up being, we can divide it over to make it a 1.
Why? Because it's negative. Does the fact that it's Y is first mess anything up?
It doesn't mess anything up. It tells us what direction it opens in.
Oh.
So if we think of the C as just having, or the Z having just a constant value, a positive constant value, and we divide it over to the other side, we get the equation for a hyperbola that opens in the positive and negative y direction. The XZ trace. If you just disregard your y's,
Would be the x squared over x squared equals c.
but you should keep your negative as well. Z equals negative x squared over a squared. And what's that shape? Nope. It's not a hyperbola. It's a parabola, right. Parabolas always open in the direction of the linear variable. So it's going to open in the z direction. And because the coefficient is negative, it's going to open in the negative z direction. And then the YZ trace. What's the equation look like? It's going to be a parabola. What's the equation? What's the equation?
Z equals negative y plus squared over x b squared.
Z equals y squared over b squared, which is a parabola again. And what did we say it opens? Positive z. So the name is hyperbolic paraboloid because our traces are hyperbolas and parabolas. So hyperbolic paraboloid. I already wrote that at the top. Adam gave it away.
Sorry.
Drawing this thing is absolutely crazy. And I'm not going to draw the XYZ axes because that's just going to mess me up even worse. I don't even know where to start. So in the YZ trace, we've got a parabola opening in the positive z. So there's my upwards parabola flat against the board. That would be like the seat of the saddle that you sit on. In the XZ trace, which is cutting into the board, there is another parabola that opens down. And that is the piece that would like go over the horse's back. And then the XY trace the XY trace is hyperbolas. So off of these, we've got these little hyperbolas.
Looks like a macaroni noodle. We'll cut it in half.
Huh?
Looks like a macaroni noodle cut in half.
A macaroni noodle cut in half.
Yeah.
I hate you.
So it's just have it done.
So mine is terrible.
Staple pretty much to our desk on that. A little bit.
Yep, that's good as it's gonna get.
Just like you take a plane and you just twist it. So it's all over.
Kinda. All right. Now I'm gonna pull up a better picture. We have some beautiful pictures in the book, but how many people have a book that covers chapter 12?
I don't think we ever had a book.
Exactly.
I use the Internet Explorer.
It was the first thing I saw. I like that one. It technically goes forever in both directions. What's even nicer is I can find one that we can rotate and like move around, and then we can see all the different traces. How when we look at it from one side, we see a parabola that opens up, and then when I spin it, we see a parabola that opens down. I kind of like this one because if you look right there in the middle, and you can see on Adam's also on the board, right there in the center, like right where you would sit on the saddle, from one perspective, it looks like it's a minimum value. It's like the low point of the parabola. But if you spin that and you look at the exact same parabola from the other perspective, it looks like the maximum point. It looks like the vertex, the max vertex of the parabola that opens down. So that's a special kind of point called a saddle point. It's actually called a saddle point. And we're going to learn about it in a couple of sections. So from one perspective, it's a maximum, but from another perspective, it's a minimum. It all depends on which plane you're looking at it from. So it's really not a maximum or a minimum. It's a saddle point. We're not going to draw these. We just want to see if we can identify what they are. I'm going to do 2 more. I just don't want to move the screen yet. The exact order of the variables might not be the same because changing the order of who's positive and who's negative might just change the orientation of the surface. A lot of the examples I did, I made it so that the orientation was always like up and down in the Z direction. But if we just change the order, it might go left and right in the Y direction or forward and backwards in the X direction. And that's perfectly fine. So the first one is y squared over 4 plus z squared over 9 minus x squared over 16 equals 1. So they're all squared. That's an important thing to note. There are a few that had left a variable not squared. They're all squared here. There's one subtraction, and it's equal to 1. You could always go through your traces really quickly and see what the traces look like. So if x is 0, we've got y squared over 4 plus z squared over 9 equals 1. What's that shape? It's an ellipse. So the yz trace is an ellipse. The xz trace, if we cover up the y, is z squared over 9 minus x squared over 16 equals 1. It equals 1. So it's not going to be lines. It's going to be a hyperbola. So far we've got an ellipse, we've got a hyperbola that opens in the z direction. And then the yz trace. Did we do yz already? And then xy trace is y squared over 4 minus x squared over 16 equals 1. Is another hyperbola that opens in the y direction. So we've got hyperbolas opening in the y, hyperbolas opening in the z, and then ellipses in the yz. So we've got 2 sets of hyperbolas and ellipses.
Hyperbola. Would that be the hyperbola of 2 sheets?
It was either 2 sheets or 1 sheet.
1 sheet?
It's 1 sheet. 1 sheet has 1 subtraction, 2 sheets has 2 subtractions. And then another way to tell is the hyperboloid in 1 sheet has your hyperboloids opening in different directions. And the hyperboloid of 2 sheets has your hyperbolas opening in the same direction. So both sets of hyperbolas are opening in your hyperboloid of 2 sheets. They're both opening like in the z direction, or they're both opening in the y direction.
So this is the nuclear reactor.
This one's our nuclear reactor. This is going to look like Sharon Harris. The ellipses are in the YZ, which means it's opening in the X direction. Okay, so it's Sharon Harris laying on the X-axis. Four x squared plus y squared plus z squared over 2 equals 1. They're all squared. It's all addition, and it's equal to 1. Don't really worry about the coefficients. Those aren't going to matter. This one's an ellipsoid. Yep. Ellipsoid is the only one where they're all squared, all added together, equal to 1. All of the traces are going to be ellipses. This one I didn't write exactly the same as the format I gave you. It's not going to be a hyperboloid of one sheet. Because if we move everything to the same side, what's going to be left on the right-hand side? A 0. So if you want to rewrite this, the only time that we ever left a variable alone on the other side was if it's a linear variable. And that's not a linear variable. So we could move it back over to the left. And if we do that, it's going to be equal to 0. So it's going to be an elliptic cone. We're going to have ellipses in the xz plane. And we're going to have radial lines in the xy plane and the yz plane. All right, one more. Y equals x squared over 16 minus 4z squared. It is a hyperbolic paraboloid.
Sounds smart. So when you go plus and nothing, just have it all forever.
If we set y equal to a constant, we've got hyperbolas in the xz plane. If we set z equal to 0, we've got parabolas in the xy plane. If we set x equal to 0, we've got parabolas in the yz plane. So we've got two different sets of parabolas, and we've got a set of hyperbolas. So this is our hyperbolic paraboloid. So instead of just kind of randomly memorizing the format for these equations, it's best to do the traces. That's going to be helpful to know what those conic sections are, and then use the conic sections, the parabolas, the hyperbolas, the ellipses, to help you. That's also going to be helpful in the next chapter when we start doing multiple integration, because we're going to have to know those traces to help us figure out bounds of integration. So the traces are really important.
And redo that. My sister got it for me for Christmas. Very nice.
So a few days ago, last week, probably a week ago, we talked about polar coordinates. Polar coordinates are, no, I actually don't know where it is in this book. This book is very out of order. Exactly.
Even math doesn't like that.
It's in the order of my notes. The order of the textbook doesn't always make sense. And then if you compare different textbooks, they will put things in different orders. So the order doesn't usually make it. I mean, they try to make it make sense, but it doesn't always matter.
That was like physics, because we had to backtrack sometimes.
Mm-hmm.
Did you guys ever figure out what
I need to talk to Ms. Pitt about that. There's nothing we could probably do about it in the summer, but we've got it on the schedule for the fall as well, so we need to fix it for the fall. No, I'm not going to do it for the summer. So we already talked about polar coordinates, which are two-dimensional. We can convert from rectangular, which are x and a y, to polar, which are r and theta. And then we can extend our polar coordinates into 3 dimensions if we just attach the z onto it. And then it's technically not called polar anymore when we attach the z onto it. It's called cylindrical. So polar is the r theta, and then cylindrical is r theta z.
I couldn't think of a new coordinate for z.
No, so spherical will have a new coordinate for z though. But for the polar, which you probably, if anybody took trig here at Nash, you probably have heard of polar already because we cover it right at the end of trig. So the cylindrical just kind of extends the polar to 3 dimensions, but then spherical is most likely completely brand new, and it's going to change all 3. Well, it's not going to change all 3 of them, but it's going to come up with something brand new for z. Spherical is very similar to the latitude-longitude system that we use on Earth. Latitude-longitude has angles for how far east and west you're going, how far north and south you're going from the prime meridian and the equator. So it's very similar to that, except in spherical, we don't use the prime meridian and the equator. We would use our axes. So spherical is specifically for 3 dimensions. It doesn't have a 2-dimensional counterpart the way that polar and cylindrical do. A spherical is specifically for 3 dimensions, and the coordinates are rho, theta, and phi. All Greek letters, yep. So that the one that looks like P is the letter rho, R-H-O. And that's always the first coordinate. In just a second, I'll tell you what these are. The second coordinate is theta, and that is the exact same theta from polar and cylindrical. So that one is not going to change. Huh? Last one is phi or phi. Either one.
It was W.
Yeah, omega looks like a W.
Billy's always calling it W and it's an F, just cussing at him.
I did that in analysis. We used epsilon a lot, and I kept calling it E. And my teacher's like, it's not E, it's epsilon.
And you got it, it's really just close to sigma.
It was a lowercase.
Oh, yeah.
And then we got like, what is it, the symbol for ohms, whatever it is,
That's an isn't that a? It looks like,
the tower and for
isn't it that?
Yeah.
What is that?
That's,
Isn't it capital Omega?
That's why, okay.
Yeah.
That's why. So W is the lowercase omega, okay.
Yeah. W is lowercase omega. I think this one's
I always
capital
think that's
omega.
Omega, and I was confused when he started calling W omega.
Yeah, because Greek has lowercase and capitals. Some of them match and some of them don't. I think that's capital Omega.
we use that.
Okay, so we've got rho, theta, and phi. I say phi because that's what I was taught. If you've used that before and you call it phi, that's perfectly fine. And you will hear either one, huh? Fine. No, phi is not correct. You can call it phi or phi. I don't really care. Huh? I've never heard it called phi before. I've heard phi and phi. I was taught phi, so that's just what I go with.
It's an accent.
I was actually taught in Texas to call it phi. All right, so here's what these things mean. So the rho is the three-dimensional distance of the point from the origin. So we're going directly from the origin out to our point, straight there, and we want to know what that distance is. It serves the same purpose as the r, except r is two-dimensional in polar, and rho is three-dimensional. The theta is the exact same theta we had in polar and cylindrical. Theta measures the angle around the xy plane, okay? And if anybody is familiar with latitude and longitude, you gotta think about it for a second. What measures east and west? Longitude. So the theta is similar to longitude. It always measures it counterclockwise with respect to the positive x-axis. So the positive x-axis is 0, and then it goes counterclockwise from there. Exactly how we learn in trigonometry, okay? So this is just an angle in the xy plane measured counterclockwise from the positive x-axis. And theta can range anywhere from 0 to 2 pi.
Oh, so we don't really do degrees,
Typically we do radians. Typically we do radians here. The phi, let me write, similar to longitude. The phi is the angle measured from the positive z-axis. So this is what's giving us our third dimension. It's the angle measured from the positive z-axis and then down. So this is similar to latitude, but 0 is marked in a different spot. In latitude, 0 is marked at the equator, and then you can go up or down from there, north or south. Phi, 0 is the positive z-axis, and then you go down from there. And we only need to allow phi to range from 0 to pi. There's no reason to ever go past the negative z-axis because that's only going to take us around to the other side of the graph. If we need to go around to the other side of the graph, we'll use theta to take us around to the other side of the graph. Okay? Because theta is the one that can go all the way around. So phi only needs to range from top to bottom. We don't need to let phi go around to the other side. If that ever needs to happen, we'll have theta take us around to the other side. So phi is only going to ever range from 0 to pi. So 0 would be the positive z-axis and pi would be the negative z-axis. So this is similar to longitude, but 0 degrees is in a different spot. But it's kind of measuring where we are north and south. Latitude. Did I just say longitude?
Yep.
I'm sorry. I meant latitude. Questions so far? No? Okay. So rho is just a distance. So it's just distance formula to figure out rho. So if we know x, y, z, and we're trying to get rho theta phi, rho is just the distance from 0, 0, 0 out to x, y, z. So to get that, all we have to do is our distance formula. But since it's always the distance from the origin, one of the points is 0, 0, 0, we're just subtracting zeros from those coordinates. It's really just square root of x squared plus y squared plus z squared. The theta is exactly the same as what we used in polar. It's tan inverse of y over x. You just need to be careful about your quadrant, what quadrant the x and the y are in. If you use your calculator to help you with this, the calculator is not always going to give you the correct quadrant back. Phi is cosine inverse of z over the square root of x squared plus y squared plus z squared. And you shouldn't have to worry about your quadrant with phi, because if it's positive, it'll come back quadrant 1. If it's negative, it'll come back quadrant 2 with cosine inverse. And we just use 0 to 90 for positive values and 90 to 180 for negative values, quadrant 2 values. So it's really just the theta that we need to be careful with, because theta can go 0 to 360. But our calculator doesn't give back all the possible 0 to 360 values for tan inverse. So that phi formula, I want to try to show you really quickly where that comes from. So if I have this point here, x, y, z, in space, the rho value is if we were to connect the point directly to the origin. Which is square root of x squared plus y squared plus z squared. I'm marking that one because that's part of the phi calculation. What?
It looks similar to like integration problems. Oh, this and that. Yeah.
If I connect this thing back to the z-axis, that's the z-coordinate in my point. What I'm looking for, this is the phi angle right there. That's the angle that we're coming down from the positive z-axis that we're trying to find. So what we know is the z-coordinate, and we also know the hypotenuse. This is a right triangle. In that right triangle, what would we call this side right here? In trig, adjacent side. That's the adjacent side. So this is adjacent, this is hypotenuse. And what trig function uses adjacent and hypotenuse? Cosine. So to calculate phi, cosine of phi is adjacent over hypotenuse. So that's where this phi formula comes from. Phi is cosine inverse of z over rho. Rho is the hypotenuse there. I don't want to put rho in there because I'm trying to write these conversion formulas where the right-hand side only has x's, y's, and z's. But technically that denominator is just the rho. So that's how we find rho, theta, and phi if we know x, y, and z. Also, the theta, if I connect my point to the origin just on the xy plane, here's the positive x-axis, and there is the point connected to 0, 0 in the xy plane, so this would be my theta. So that's how far I have to go out to get to the point. This is how far I need to rotate in the XY plane, and then this is how far I need to come down from the Z-axis to get to that spot. So all three of those combined will help us locate a unique point in space. To go backwards, so these are to go from XYZ to rho theta phi. If we want to go rho theta phi to XYZ, the formulas are a little bit different. And then we'll have just a few more minutes to try a couple conversions. X is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And Z is equal to rho cosine phi. These formulas are also useful if we want to convert a function in terms of XYZ to rho phi theta if we have to convert the XYZ variables individually. So if we had to go through and replace X with what it is equivalent to in terms of the spherical coordinates, and replace Y with what it's equivalent to in terms of spherical coordinates, and replace Z, we would use these conversion formulas. So these are called spherical coordinates because anything that is spherical is going to be a lot easier to write in spherical coordinates. So think about what we talked about last week or the week before. If a variable is missing from a function, that means there's no restrictions on it. So a sphere goes all the way around the xy plane. So we wouldn't need a theta in that equation because there's no restrictions on the theta. And we would go all the way from the top, z, positive z, to all the way to the negative z. So we wouldn't need a restriction on the phi either. We would use all possible values of phi. So we wouldn't need a phi in the equation either. So a sphere in 3 dimensions would just be rho equals a number. A sphere in 3 dimensions would just tell us how far out to go from the origin. X squared plus y squared equals z. What's that surface? X squared plus y squared equals z. Nope. It's a 3-dimensional surface. It's not a plane because of the squares. not a piece.
The only one. Oh, my bad. Elliptic parabola.
It's an elliptic paraboloid. Mhm. If z is a constant, we would have ellipses or circles in the xy plane. Our xz trace would be parabolas, our yz trace would be parabolas. So we have hyperbolas and two parabolas. It's an elliptic paraboloid. Hyperbolic paraboloid. I just messed that up. What did you say it was, Adam?
It says elliptic.
It's an elliptic paraboloid. It's an elliptic paraboloid. If z is a constant, we would have ellipses. Technically circles because they don't have different denominators. And then our other two traces are parabolas. So this is the one that looks like the bowl. We're going to convert this to spherical coordinates. If you can, we like to replace entire chunks of stuff. And usually the chunk that we can replace is x squared plus y squared plus z squared. X squared plus y squared plus z squared is going to be equal to rho squared. Okay? But we don't have x squared plus y squared plus z squared in this one, so we can't replace a chunk. We're going to have to replace the variables individually. So we're going to have to replace x with rho sine phi cosine theta. We're going to have to replace y with rho sine phi sine theta. We're going to replace z with rho cosine phi. And we're going to do a bunch of simplifying. If possible, spherical equations like to be solved for rho. Okay? So if at all possible, when we're done, we would like this to say rho equals something. So I'm just going to start by replacing. And then we'll try to simplify after that. So x is rho sine phi cosine theta. And the equation says we need to square it. Y is rho sine phi sine theta. And the equation says we need to square it. And then z is rho cosine phi.
Do you do all your p's starting out with the circle point?
I do rows like that. Because rho is not p.
Or how do you do your p? In your L, do you go bottom, top, top, bottom?
What kind of L?
Lowercase? Like right now.
If I'm writing fast, I usually do a cursive L.
Regular L.
Top to bottom.
Bottom, top.
You do bottom to
What
top?
about like a lowercase?
Are you left-handed?
No, right-handed. What about like a lowercase I?
That seems like a left-handed thing.
Lowercase I do dot and line.
That's wrong.
Why would you go down and then have to come back up?
Why are we talking about this?
I'm sorry. I'm sorry. It's just.
Why don't you go up and then go down a bit?
How do you know where to put your dot until you've got your line drawn?
And the line goes right below the dot. Anyways.
Do you cross your T before?
No, that's impossible. I never forget to dot my I's.
I don't ever forget to dot my I's.
There you can't cross it.
This is now just a trig simplification problem. Was that our favorite part of trig class? We're going to go ahead and square everything that says to square. The stuff with the squares, there's no addition or subtraction inside, so we can distribute the squares. If there's addition or subtraction, you're not allowed to distribute squares. But here, I don't see addition or subtraction inside those parentheses, so we are allowed to distribute the squares. So this is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals rho cosine phi. What is your suggestion, Adam? Did you have a suggestion?
Oh,
What?
yeah. Below, rho squared, sine squared, phi.
Right, both of the terms on the left have a rho squared sine squared phi in common. So if we factor it out, we're left with cosine squared theta plus sine squared theta. Which is special. It's equal to 1. Cosine squared theta plus sine squared theta is equal to 1. And multiplying by 1 leaves just rho squared sine squared phi equals rho cosine phi. The theta disappeared from the problem. That means whatever this surface is, it has no restriction on theta. It goes all the way around the xy plane.
We're solving for P.
Yes.
Let's just subtract. Subtract. You gotta subtract.
You could subtract.
Won't do anything.
You could subtract. To be 100% mathematically accurate, in terms of rho, this is technically a quadratic equation. So we could factor a rho out. And if those two things multiply to make 0, then one of them is equal to 0. Either rho equals 0 or rho sine squared phi minus cosine phi equals 0. We need to solve that second equation for rho. Add your cosine over, yep. So rho sine squared phi equals cosine phi. We want to solve for rho. We want to, so usually whatever we're solving for, we leave it alone and we move everything else away from it. So divide by your sine squared. And I'm going to rewrite that as two different trig functions. Did you say secant? Cotangent, cosecant, yes. Or cosecant, cotangent, however you like it. The rho equals 0 technically is important because cotangent and cosecant are both undefined at 0. So the rho equals 0 is important to fill in that hole. So we have to represent it with two equations. We'll talk a little bit more in the next section about limits and filling in holes. What we were able to do here, though, if the original function had 3 variables, and when we changed it to spherical, it only had 2 variables. So that's a little helpful. And if we had to integrate this and find volume or something with this function, being able to eliminate a variable would be very helpful. Yep. One thing I want to tell you really fast as we pack up and head out, there is homework posted. Yes. I am going to change the due date because it goes through section 3, and we're definitely not through section 3. We are done with section 1. Section 2 talks about graphs and level curves. The first thing it talks about is finding domains. When we find domains, it's very similar. We use the same rules as we did in algebra, where, the limits are in section 3. Limits are in section 3. So we'll get to domain and limits on Thursday. But when you do domain, in algebra, when we do domain, we almost always want our answer in interval notation. Now that we're working with several independent variables, we're not going to be able to write our answer in interval notation. So domain here is always going to be written in set builder notation. So for 12.2, so this is just in case anybody is stuck on the homework or wants to be able to do a little bit more homework. For domain, we're going to use the same rules as algebra, where we can't ever divide by 0, we can't take square roots of negatives. For logs, we can't do log of a negative or 0. It's all the same algebra rules about the types of calculations we're allowed to do. The only difference is we're not going to be able to actually solve for numbers we're allowed to use and not allowed to use. Most likely what's going to happen is we're going to solve for some sort of relationship between the x's and the y's. So if we have a function of x and y, this is the same thing as saying that I have a z equals. We're about to be done, sorry.
No, this is.
So if this was f of xy, we've got two independent variables. Z is the output variable. And we had 2x over x plus y. So I just wanted to show you one fast example of how we would write our domain differently for these types of problems. So what do we need to be careful of in this type of function when we're thinking about domain? All we're worried about is domain right now.
Just zero.
0 in the bottom, right. We need to make sure that x plus y doesn't come out to be 0. So we're not actually solving for numbers we are and are not allowed to use. What we're solving for is a relationship between our independent variables. So what we're really solving for here is what y is or is not allowed to be usually in terms of x. So if I solve that for y, or if I solve it for x, y is not allowed to be negative x. So the domain for f is the set of all values x, y. This is set builder notation. It's the set of all values x, y such that y cannot be negative x. So the brace means we're dealing with a set of numbers. Since it's a function of several variables, we've got two independent variables. So our domain consists of ordered pairs. That vertical line means that we're about to start stating the restrictions. So it means such that. And then after the vertical line, we say what the restrictions are. This is called set builder notation. So this is read, the domain of f is the set of ordered pairs x, y such that y is not equal to negative x. We would never write these domains in interval notation the way that we did in algebra. It's always going to be a relationship.
So is 0 implied there since 0 doesn't have a negative?
We would not be able to use 0, 0.
No, it's also,
We would not be able to use 0, 0.